Air undergoes a polytropic compression in a piston cylinder assembly from P1 equal to 1 bar and T1 equal to 22 degrees Celsius to P2 equal to 5 bars. It's being compressed, right? Employing the ideal gas model, determine the work and heat transfer per unit mass. Essentially, we're looking for W and we're looking also for Q. Okay, per unit mass if we are given that N is equal to 1.3. Let me sketch first for the problem. Okay, so we have here the cylinder being compressed. Okay, so we expect W to be positive because heat is being what, and the work is being done to your system. So from 1 bar naging 5 bar, it's being compressed, and then the temperature more or less we don't know yet as of the moment. But what we know is it's N equal to 1.3. Polytropic meaning PV to the N is equal to a constant in this case, and that constant, that N is equal to 1.3. So PV to the 1.3. Pag isentropic, yung N mo will be equal to gamma, which is Cp over Cv, which is normally 1.4 for air. PV or for polyatomic gases equal to K. So now let's try to, I think work is solvable, right? Oh wait. Okay, I think we can solve for work. Are we given with volume? Oh no, wait. Are we given with volume? Not really. Well, what we know is pressure 1 and temperature 1, right? Okay. But since we're looking for per what? Per kilogram of something. So let's have here T1. We know T1 to be 22 degrees Celsius. We have P1 um to be what? To be 20, no, P1 will be 1 bar. I think we could assume a mass. In this case, since we're looking for work per kilogram of air, we can assume that mass is equal to 1 kilogram, or in that sense, number of moles will be, we're using, I think we need to use 29. Okay, for air we're using 29 in here, 28.8, but I'll just approximate that to 29. So number of moles for that will be 1000 gram divided by 29. It's equivalent to 34.48 grams. Okay, no, not 34.48 grams, but 34.48 moles. And I believe from the ideal gas law, okay, we can solve for V1, right? How do you solve for V1? Well, the ideal gas law says that PV is equal to nRT, and therefore V1 will just be equal to N1RT1 over P1. Okay, in that case, N will be 34.48, R will be 8.3145, T1 will be 22 plus 273.15 divided by P1 will be 100,000 bar. Convert that to Pascal. 100,000 bar. That gives me a volume of, the initial volume is 0.846. Okay, 0.846. Let me put 1. No, not 0.89 na lang. 0.89 m, 0.85 m cube. Or shall we say 0.846? 0.846 m cube. Okay, that's V1. Okay, so I think we now have that. So not much of a problem really. Okay, so I think we can now solve for work. Work is just equal to the negative integral of P dV, right? And evaluate this simply from V1 to V2. And how can we express P in terms of V? From here, clearly, we can see that P is equal to, from that, you can really see that P is equal to what? K over PV to the 1.3. Okay, so in this case, I'll have here negative integral of K dV over, no, there's no P there, but only one. V to the, not 1.5, but 1.3. V to the 1.3. Okay, and then that will lead to, well, negative K integrate mo yung 1 over v to the 1.3, well, that will become v to the negative 0.3 over negative 0.3 taken from v1 to v2. Okay, now work will therefore be equal to what's 1 divided 0.3? That's 3.333 times v2 raised to the negative 0.3, there's k here, okay, minus v1 raised to the negative 0.3. Okay, close to there. Now, the thing is, wait, that's v2, and we know the v1, right? 0.846, but we don't know v2 yet. However, since we know that this is a polytropic process, pvn is a constant. Okay, we can solve first for k. What is k? K is equal to p1. Let me choose a different color. So using that principle, I'll just have it here. K will be equal to P1. I'll have that P1 to be, okay, P1 is 100,000. 1 times 10 to the 5 Pascal. V is equal to, V1 is 0.846. 0.846 raised to the 1.3. That's equal to K, which is in this case that k is equal to 0.846 raised to the 1.3 times 1 exponent 5, wait, 0.846 raised to the 1.3 times 1 exponent 5, that gives me a value of k 80,460, okay, 80,460. And how do I calculate for V2? Okay, so I think K here is already known, so I'll have here 3.333 times 80,460. Now, how about V2? Well, if P1 V1 to the 1.3 is equal to K, also this will still be equivalent to P2 V2 to the 1.3. We know P2, 5 bar. Okay, so how do we compute for V2? Well, that's K. Divide mo lang yan ng P2. So, in that case, V2 will then be equal to, okay, solve mo lang yung V2 dyan. So, from there, I think you can see that V2 from there will just be equal to K, which we already know, over what? P2. Then, raise mo siya sa 1 over 1.3 para makancel yung naka-express mo dyan na 1.3. Okay, I hope na nakuha yan. Okay, so in that case, we know K, 80, divide P2. P2 mo, 5 bar or 5, that's 500. Kasi yung isang bar, express in Pascal, that will be 5 times 100,000. So, 500,000 Pascal. Okay, divide mo yan. Then, raise mo siya sa, raise to the 1 divide 1.3. Okay. And that gives us that V2 mo, yung after compression, V2 will be equal to 0.245 m cubed. Okay, so yun, nakuha na dun yung V2. So in that case, V2 will be 0.245 m cubed raised to the negative 0.3 minus V1, 0.846 m cubed raised to the negative 0.3. So ideal gas law yung ginagamit mostly sa una, then yung given na PVN to solve for the V2. Okay, and then this will lead us to 0.245. Okay, so these things when multiplied together will supposed to give me 126,986 joules of work, or that's equivalent to 127 kilojoules. Okay, that's the work done by the surrounding. A positive means the surrounding do work to your system. So PdV pa rin, pero yung idea lang paano mo hahanapin yung final volume. So using the PV na binigay, or paano hahanapin mo yung initial volume using the ideal gas law, assuming of course that it's per unit mass. You assume a mass of 1 kilogram. Okay, now how about the second question? We're asked here to calculate for the heat transfer. What is Q then? So there's no way we can solve for Q since we're not given with the temperature. What is the heat transfer coefficient if we use the heat transfer principle? Now we'll just go back to our original equation. Okay, we'll then be going back to, okay, delta, wait, let me change color for this. Going back to the equation, delta U is equal to Q plus W. I think we already have solved for W. And to solve for Q, we can just solve first for delta U, right? Well, how do you solve for delta U? Assuming that this air is an ideal gas, delta U will then just be equal to number of moles times CV times delta T. Okay? What's the initial temperature? 22. What's the final temp? Sad to say, we don't know yet as of the moment, but I think we could calculate that. Right? Can we calculate the final temperature? I hope so. Since we are given with P2, we are given with P2 equal to 5 bar, we are also now able to calculate for V2, which is in this case 0.245 m cubed. Okay. We also know the mass, or the number of moles. Since it's a closed system, the number of moles doesn't really change. 1 kilogram, or that's approximately equal to, that's N, same as N1, 34.48. Okay. And then, we know this already, PVN, so we can actually solve for T. How do you solve for that? Using the ideal gas law, or gas equation. PV is equal to nRT. So T will simply be PV over nR. Okay, PV, P, that's 5. So T will just be PV over nR. And in that case, P is 5 bar, so that's 5 exponent 5. That will make it 500,000 Pascal. V is 0.245, and it will be divided by 34.48, and R will be 8.3145. It will give me a value of 427.3 Kelvin. That's the final temp. Okay, so I think we can then solve for delta U, right? Number of moles, we have 34.48. What is CV? In this case, air is a diatomic, so we could simply use that 5 halves R. 5 halves of R, which is in this case, R is 8.3145, and delta T will just be T final. That's 427.3. Okay? Or let me convert that to, what is this in Celsius? The minus 273.15, that gives me in Celsius to be 154. Okay, 154 point, or 154 degrees Celsius, just rounded off. 154. Okay, so meaning I really committing here a lot of rounding off error, but essentially we're looking here for the magnitude of the value only. 154 minus the initial temp. We start with 22 degrees Celsius minus 22. Essentially, delta U in this case will be 154 minus 22 times 8.3145 times 5 divided 2 times 34.48. It gives me a value of, well, again, 154 minus 22 times 8.3145 times 5 divided 2 times 34.48. That gives me 94,605.7 joules. Okay, or essentially that's what? 94.6 kilojoule. And Q therefore will just be equal to delta U from that equation. This is from what? The first law of thermodynamics. Delta U minus W. So delta U is 94.6 kilojoule. The work done, W is 127, rounded up only 127 kilojoule. It gives me a Q of, what's that? 94.6 minus 127. It gives me negative 32.4. Okay, negative 32.4 kilojoule. which is more or less close to that, the real answer. Meaning heat is being what? During this process, since actually this one will heat up, we expect that heat will be leaking out, will leak out to the surrounding, to your surrounding because the temperature will build up in the air inside will be heating up. So that's it. And I hope that you follow the process. If not, there are actually predefined formulas for this one, but I don't really suggest doing that because at the end of the day the things that you learn from here, it will really be better if you know how to really use the ideal gas law, for example, to solve for V1, how to use the given polytropic process to solve for V2, and how to solve for T2. Okay, T2 using ideal gas law again. Okay, back to the ideal gas law. Thank you.